computer. That's what I want. Okay. So have you gotten 2 requests to be recorded? Or just one? Okay, just one. Okay, I believe that we are going ahead and recording. So this being said, let me share with you a few things. Let me share with you, first of all, if I can put up a Google meeting, the conversion from one earth to another earth. And I think I'd like you to study this because this is fundamental in doing a bunch of stuff. Let me go ahead and get the conversion of one earth into another earth here just in a second. And I will need to share the screen. This, by the way, is linked on the page that we share with Google Sheets. Okay, here is the definition, and you can all see this, I suppose. This is the definition of the first earth, and I want you to know that I spent a lot of time doing this. Whoop, I hit something that I shouldn't have. Spent a lot of time doing this in Google Equation Edit, which is not the most friendly equation edit in the world. So I hope you appreciate that. So this is the definition of the earth that I gave. It's the 1 over the square root of 2 pi. And then there's all these, then there's all of the other stuff. Okay, for some reason my there it is. Okay. Okay, it doesn't let me draw on here, so probably there's a way I can do that, but I'm not going to do that. I'll just kind of point. So here is the definition of the earth, the one that I gave to you. We want to s generated to e to the minus, say, z squared. So I forget who worked it, but somebody worked it and they said let z is equal to y over root 2. You did, then dy is equal to root 2 dz. And then the thing you have to do is figure out what happens to this these integration limits. So if y is equal to x, y is your integration limit. If that's equal to x, then z is equal to x over root 2. That follows from this expression. And so this is a redefinition of the earth by substituting the upper limit, by making sure that the dy is replaced by root 2z. And then what we have is we have e to the minus z squared, which is the form that we wanted for the other definition of the earth. And then if we simplify that, that becomes this. That becomes this expression. Now the other earth didn't have a 1 over root pi here. It had a 2 over root pi. So we're going to force that to be 2 over root pi and then multiply out front by a half in order to eat up that 2. And this becomes 2 over root pi times this expression. Now this is exactly the expression for the other earth. And so the result is 1/2 earth, the second earth, except that instead of the upper limit is x over root 2. So earth 1 of x is equal to 1/2 of earth 2 of x over root 2. So that's going from one earth to the other earth. How do we go backwards? Well, to go backwards, any questions on that? See, the thing is that we, there's a tendency to stumble over this, yet this is stuff that you learned way back in calculus, variable substitution, manipulation of integral relationships. And for some reason, we lose that these days, I believe. So it's relatively straightforward. Now, this is given earth 2, how you get back to earth 1. And oh boy, let's see. Why do I not like this? Earth of 0 should be 0. Oh, no, that's okay. That's okay. Okay. So I thought I saw a little failure of a sanity check there, but I checked myself and it turns out that the sanity check did explain itself. So this is earth 1 in terms of earth 2. How do we get them backwards? Well, we set W is equal to x over root 2 motivated by the argument right here. W is equal to X over root 2. And then we can manipulate everything in terms of W and then get ERF2 being converted back to ERF1. So this is linked into the Google spreadsheet that we all share and know and love. Let me get this up. And so if you go down to here and you see the convert, and you see the convert the MATLAB ERF to my ERF, the solution is in this Google Docs, which you see here. So there's a link on the spreadsheet to the solution for that. Okay. Okay, all well and good. Any questions on that at all? Okay, now there's one of these that we saved for next time, which was, let's see, I forget, there was a change that we made. Does anybody remember which one it was?
It was 13.
Okay, so it was this one?
Yes.
Okay, so we'll put that on next time also. And I'll go ahead and change that on the spreadsheet so we have that. Now, I want you to notice that I've added some homework here. One of them is to evaluate the optimal 20 questions query for when the probability distribution is a third, and a third. So you imagine that you have, you have, I don't know, 30 squares, 10 of them are A, 10 of them are B, 10 of them are C, or something like that. And you want to identify the color of, you want to identify the letter with the fewest number of queries, like we did last time. Remember that we showed that interval halving was the quickest way to do that. And so I think for this one, it's going to be relatively easy. There's another one here, which is harder. Do you see this? P is equal to 1/8, 3/8, 1/10, 2/10, and 2/10. Suppose that you had this probability distribution. What happens? What is the value, or what is the procedure for optimally choosing when the distribution is given by this? Okay. Now, it's this is going to be much more difficult. Now, your sanity check is that in each one of these cases, I ask you to compute the entropy. Now, the entropy, of course, is H, and it turns out if you have the right answer, the expected value of the number of questions will always be between H and H plus 1. If you choose the optimal answer, then the expected value of queries will always be between H and H plus 1.
Is that off, or is that valid for the homework, or just for like every case?
That's valid for that's value. That's the answer for every case. No matter what question you get, the number of queries should be between the entropy and the entropy plus 1. Now, before we found out that it was exactly the entropy. And it was the entropy because exactly the entropy because I chose all of the probabilities as 1/2 to the nth. There's a name for that sort of probability, I forget, but when you have 1/2 to the nth, it turns out you can apply interval halving straightforwardly there because all the probabilities are in the form 1/2 to the nth. But in this case, we don't have that. We have a probability of a third, and a third, and here we have all sorts of a mixture. So how do we best apply that? The other thing that we did is we talked about the expected value of 2 to the minus length of n, the expected value of this. Remember, this is the number of steps that were required in order to go to the optimal solution. And we showed the expected value of this was also between H and H plus 1. So this is a check once you get an algorithm that the solution is going to always be between H and H plus 1. This is one of the elementary properties of entropy. Entropy has a lot of interesting properties, but we're not going to get into those because Well, simply this is a course in probability. We could talk about more about entropy and its fascinating properties in information theory.
Dr. Marks?
Yes.
So is it possible to have a non-optimal, like have multiple cases of a solution to be within that boundary between h and h plus 1?
Yes, there is more than one way to get the h and the h plus 1. Yes.
So then,
Many times, however, it will be unique, and I think in many cases it will be unique. Like for example, the 1/3 and 1/3 and 1/3. You can probably work this one out in your head if you look at the 1/3, 1/3, 1/3, and the question is, which one do you choose first? Is it this 1/3? Is it the second 1/3? Is it the third 1/3? And so that in itself shows you that there's a number of solutions, but these are kind of coincidental due to the numbers of the problem. In general, it can be unique.
okay.
Okay. So that's an interesting property of this, and also add to this this result. So let me actually add this in right here. Insert one above, and then I'm going to it's this one, right? And go down and paste it. Okay. So that will be what we will do next time. Any questions on that, or does that make sense to you? Okay.
Dr.
So
Marks,
yes.
I'm a little confused about what you're looking for with the 2 to the minus length n case.
Okay.
I know we talked about if you sum all those up, that should equal 1. But I guess what else can we show from that here?
Is the expected value of that. You add them up and they add to 1, which means that you can always think about 2 to the minus L as a probability density function, right? Because they all add up to 1.
Right.
So if they are a probability density function, and 2 to the minus L is the probability associated for L, a search path of length L, you can compute the expected value of that.
Oh, okay.
And that expected value is going to tell you what the result is.
Okay.
What I would suggest you do, if that still confuses you, is to maybe download the PowerPoint where we go through that simple example.
Yeah, I was looking at the PowerPoint. I guess I must have misinterpreted something.
Oh, okay. Okay. Well, okay. So yeah, let's go ahead with that, and let's assume that you can get that result, and we'll see how it goes next time. Okay.
Mhm.
Okie dokie. Any other points or questions or anything else? Well, very good. So with that, let's go back to the functions of a random variable. Now, let me share my screen again. By the way, I'm in Corpus Christi now, so you'll notice a different background, which is kind of cool. So this is what we ended up last time doing. If you have, no, that's not where we ended up. Whoa, we ended up way down here. Let me see. Yeah, here is where we ended up. We ended up with the idea that if you had a strictly increasing or a strictly decreasing function, if you have a strictly increasing or a strictly decreasing function, strictly increasing or strictly decreasing, that if y is equal to g of x, then you obtained your probability density function for the new random variable by taking the old random variable and dividing it by the derivative at the value where x is equal to the inverse of g. And that's where we ended up. We'd like to generalize that right now into different cases. In general, we don't have this. In general, we don't have a strictly increasing function. We have a function that wiggles all over the place, such as we see here with this g of x. And how do we do that? Well, the way we do that is through f sub y is equal to the summation of the same exact transformation that we saw last time, except that it has to be done at a number of points. You notice that there's a number of points for y here. Now I'm going to show you what I think is a very intuitive interpretation of this expression, which might look to you to be kind of strange. And here is the idea. The idea is that you have a probability density function, f sub y. Or I'm sorry, f sub x. You have a probability density function of f sub x, and you have this transformation on a random variable, y is equal to g of x. And what you'd like to do is you'd like to find the probability density function of y. Now, you'll notice this y is equal to g of x is on a Cartesian plane, which is x versus y. So it's on a two-dimensional plane. Think then of the density function for x as being along the same axis as this x-axis is here, and that the y-axis be up and down as the y-axis is shown here. The way to think about the transformation of the random variable is to bounce it off. You take a probability mass. We have a little bit of probability mass here. We have a little bit of probability mass here, and we want to bounce it off. It's almost like this is a distorting mirror, if you will. And we want to bounce it off, and we want to take all of that probability mass, and we want to place it here. And that is the idea. So think of that. We want to take the probability mass here, and that's a little probability mass here, and we want to place it here. Now let's look at this in a differential form. In a differential form, let me just check something here. I thought I know where this was coming, but I'm not really sure. Yes, okay, this is fine. So here's the idea. We have x and we have x plus dx. So the distance here is dx, right? And we would like to transform this to a place that goes from y to y plus dy. So these are little incremental changes, right? And of course, this distance is what? This distance is dy. Now, the thing is there's conservation of probability mass. And the question is, what is the probability mass here? Well, you know, if dx is small enough, we can estimate this y value here. We can estimate the top value here just by a sample. So the area here is going to be f sub x of x. That's the value at this point, right? Which we assume is very small, so it can be estimated by a constant. So if we take the area of a rectangle, it has a height of f sub x of x, whatever the value is for x here, and then it's times dx. So that's the area of the probability here. What's the area of the probability here? The area of the probability here is f sub y times dy. And we want to make sure that those probability masses are the same. So do we see that? So therefore, what we've assumed here is that f sub y, the probability mass, the second mass, f sub y of y dy, is exactly the same as f sub x dx, right? Well, notice, this is kind of cool. this says that through this analysis that f sub y of y is equal to the density, and I'm going to take this value to the other side. And I get this result just by looking at this conservation of an itty bitty increment of x and little pieces of the probability mass, and we obtained the exact same result that we did prior, that we did up here. This is exactly the same result as this, where of course this g of y is the same thing as y, so it's dy dx. So it's exactly the same result. Yet it's derived, it may be a little bit more, I don't know if it's more intuitive to you or not, but if we did this for each one of the little probability masses here, we divided up the entire x-axis into these little probability masses here, we would obtain for all values here that this is true. Now, there's a question of what happens if the if the nonlinearity is strictly increasing. You can see that the nonlinearity here is strictly increasing. What happens if it's strictly decreasing? Well, if it's strictly decreasing, then the mapping of x plus dx from x to x plus dx on this probability mass function is going to be f sub x of x this is going to map, if we turn sideways here and put a y up here and an f sub y of y here, we want to bounce this off the curve here. And we want to make sure this probability mass is exactly the same as the probability mass down here. Now it's a little bit different because x now goes as to y here, and x plus dx goes to y plus dy. Well, what does that mean about dy? It means that dy is negative, right? dy is negative. So in order to get the mass, what we find out is that f sub y of y times minus dy must be equal to f sub x of x times dx. Or in other words, f sub y, if it's strictly decreasing, is equal to f sub x of x divided by, we can see what's going to happen here, minus dy dx. But hold your taters here. What do you know about dy dx? From dy dx, it clearly shows that dy dx is less than 0, right? Since we have a strictly decreasing function, here, the derivative of y with respect to x is always less than 0. So minus dy dx is always going to be positive. So we can write it as dy dx. Since dy dx is always going to be negative. So this is the reason when we go up to expressions like this, that we always put the magnitude of dy dx, g is equal to, or y is equal to g of x. We always put things here into the into the denominator with the absolute value, because the absolute value takes care of both the negative slope and the positive slope. Everything is all well and good. So all of a sudden now we see the reason for this need for the transformation. Let me elaborate a little bit. I don't know what this is. Document recovery. I should be able to get rid of that. Close. There we go. Okay, let's view now what happens if we have a y is equal to g of x. Which is kind of crazy. And we have a probability mass function that looks like this. This isn't a probability mass function, it's a probability density function. So we have the f sub x of x that looks like this. So this has a total area of 1. And we also have the probability density function for y here, which we're looking at sideways. Well, all of a sudden, if we look at a specific point, say we're looking at this point, y, and we want to figure out how the probability mass in x transforms to this point in y, we have a bunch of contributions, right? Because we have to do a little bit of bouncing off of this between x and plus dx, right? So we have a little bit of probability mass that comes from here. So a little bit of probability mass that comes from there. We have a little bit of probability mass that comes from here, right? This has to be, this maps onto the same exact interval. So this stacks up. So we have a little bit of probability mass here, and then we have a little probability mass here that has to be mapped onto that interval, right? And each one of those is equal to the value of g, or g of x at that point, times d of x. And so these all stack up. And so we have a sum of contributions that tell us this f sub y of y, because all of this probability mass bounces off of the y is equal to g of x at a number of different points. So we have a number of different contributions. Each one of these f sub y's is equal to f sub x over dy dx. Except the problem is we have a bunch of these. We have the one right here. Let's call this x1. We have a one here which is called x2, one here which is called x sub 3, and we have one here at x sub 4. So there are 4 places which map to the overall probability mass function. So we can talk about f sub x of n, and then the derivative at that point, and then we just sum up all of those contributions. And thinking about the probability mass function as being just bounced off this nonlinear curve is a very useful way to think about probability density functions. And again, is the reason that we have let's see, where it is it? Okay, is the reason that we have this expression. We have this expression because there's a little bit of probability mapping going on at x sub 1, a little bit of probability mapping going on at x sub 2 and x sub 3. So we simply add up all of those contributions to see what it does to the resulting distribution for f sub y. So that's the general transformation on a random variable. Okay, did that make sense? Okay, good. I always it made a lot of sense to Glauco because he excused himself for a minute. Welcome back, Glauco. I was just asking whether everybody really liked the clarity of the explanation. So I'm sure you did. So, okay, it was so clear. Okay, never mind.
It's cold here, sorry.
It's
I
cold
just
there.
get up.
Okay, okay. So therefore, that's the transformation on the random variable. And that's the way to geometrically interpret it. I love geometrical interpretations because it gives me good insight into what's happening. And if I have the geometric interpretations, I can go to the mathematics and I can do the mathematics a little bit better. Okay. Let's look at some special cases now. Here's one of the cases. What if you have some sort of function, y is equal to g of x? And this is y, and this is x, and this is g of x. And the random variables under consideration are discrete. In other words, you have a bunch of direct deltas. What happens if you have, say, a uniform probability density function over, say, four values, and they're equally probable? So this is my f sub x of x. This is my probability density function, and it's expressed as direct deltas because I like to do that. So this is what happens when we have a discrete random variable. Well, what happens here is incredibly simple. You simply bounce the direct delta off of the nonlinearity. So this one bounces off the nonlinearity, and it looks like this is just a little bit of epsilon. So that becomes a direct delta exactly with the same weight. This one becomes a direct delta exactly of the same weight. This one's going to be a little bit further. And the point is you get exactly the same direct deltas, except they are no longer uniformly spaced. So what you get then is you get, if the original function is f sub x is equal to 1/4 times the summation of n is equal to 0 to 3 of del of x minus n. That's the original density function. That's what this is, right? And let's say g of x is equal to x cubed. Then the next value is going to be equal to 1/4 times the summation of n is equal to 0 to 3 of a delta function. I'm going to go to a separate line here since I run out of space, of a separate line of x minus n cubed. So this will transform to 0. The 1 will transform to 1. The 2 will transform to what, 8. And the 3 will transform to 27. Clearly what I've drawn here is not to scale, but that's going to be the transformation. So the point is, for a discrete transformation, the answer is pretty straightforward. It just bounces directly off of the nonlinearity, and you get the corresponding discrete relationship. So that's pretty straightforward. Any questions on that? Okay. I find when there's no questions, I'm either very clear or very opaque. I'm not sure which one it is. Let's do some examples here, and hopefully these are examples are things that we can do kind of like in our head. I maintain that if we do the transposition y is equal to minus x, then f sub y is equal to the transpose of f sub x. So in other words, I'm saying this. I'm saying that if f sub x is equal to this, then f sub y is equal to the transpose of this. And I hope you can think of this as a transformation off of a nonlinearity y and x is equal to something with a slope of -1. And if you go through the exercise of bouncing off this nonlinearity, you find that you get a transpose, just like I've shown here. So that's pretty cool. So that's something we can do in our head. We get with this idea of bouncing off the nonlinearity, we can do some of these transformations in our head. Let's look at another one. Suppose we take a random variable and we add a number to it. Say we add the number 3 to it. Little s is equal to 3. So we add a real constant to it. What happens to the density function? Well, the density function is simply shifted. And you can also imagine this from bouncing off a nonlinearity. So if we have f sub x that looks like this, then f sub y is going to be exactly like this, except it's going to start at s. So I'm going to try to draw the same. Okay, that's supposed to be the same density function, just shifted over. So that's something we can do in our heads also. And you can perform this operation by choosing an appropriate nonlinearity, which I will let you figure out. If you multiply something by a, then it turns out that the density function is 1 over a times the density function. Say, for example, a is equal to 2. So you have something which is uniform that goes between 0 and 1. So you have a density function which goes between 0 and 1. And this is going to have a height of 1 in order to keep the total area under this curve equal to 1. So if we multiply by a, and let's say a is a positive number, say a is equal to 3 or 4, let's say it's equal to 3, then we know that f sub y is going to be as follows. Our reasoning is as follows. Before, the maximum value we could get was 1. Now, if we multiply it by 3, the maximum value we can get is 3. So we know that the density function for a is equal to 3 goes between 0 and 3. And we'll have exactly the same uniform value. But the problem is now we still have to give this an area of 1. So we have a 1 over 3. We have to give it a value of 1 over 3. So that's what this expression is. F of y over a means that you stretch it out by a factor of a. If a is equal to 3, you take it and stretch it out by a factor of 3, and then you divide by 3 in order to give it a total area equal to 1. And so what would be the g of x for this? Well, it's pretty simple. We would have a y is equal to a times x. So for 3, for example, we would have a line which was y is equal to 3 of x. So we would have a line with a good slope, which is greater than 1, in this case equal to 3. And in order to map the probabilities, as we talked about before, of bouncing off this g of x curve, y is equal to g of x curve, then we would get this transformation on a random variable. So all of these are examples of things that we can work out in our head that correspond to this transformation on a random variable. What about the modulus? What if we take y is equal to the magnitude of x? This is something which is done a lot when you're adding up the absolute value of errors. Sometimes the error is negative, sometimes it's positive. You want to add up the magnitudes of errors. Well, in this case, what you do is you take you take one side and flip it over to the other one and add. Let me see if I can illustrate here. Say we have a density function which looks like this. What we want now is a g of x, which is equal to the magnitude of x. Therefore, this goes down like this, and this goes up like this. Well, if we bounce it off of that nonlinearity, what we obtain is I keep losing my cursor here. What we obtain for f sub y of y is exactly the same as the positive value, because for the positive value, the magnitude of a positive value is equal to a negative value. But the negative values become positive. So this portion of the curve is transposed and flipped around the y-axis. I try to do a dash curve here. And then these two values are added up. And so this is the original function as a function of y plus this flipped function. And then we chop it off at y is equal to 0. So u is equal to a unit step. We're just making sure that we chop it off at value equal to 0. So again, if you take the modulus or the magnitude of a random variable, or the modulus, if you will, it's like taking the original probability density function and folding it about the y-axis and then adding up the results. So this is something else that you can convince yourself of by that idea of bouncing off the nonlinearity, bouncing the original density function off of the nonlinearity. What about shift and scale? I'll let you do this, but it's kind of a combination of the other two that we talked about. We have a x minus s, and we have over the a, and so you can look at that also. So what is the y is equal to ax plus s? Well, if we have x, if the value is equal to 0, if x is equal to 0, then the value is equal to s, and we have a slope of a. And this is the nonlinearity which you bounce off of, and you'll find that this is the result that we have here. So everything I've looked at has been kind of straightforward. It's been either linear or piecewise linear sort of transformations on a random variable. But the formula that we gave you initially is very powerful because it can do all sorts of transformations on a random variable. Okay, I'm going to stop sharing my screen. Why can't I show? Okay, stop sharing the screen. So are there any questions at all? Any questions? Okay, if there's no questions, we still have a little bit of time. So this is transformations on a random variable. I've gone through the simple cases. We'll give you a few more harder ones to analyze as time goes on, if you will. So let's go back to the PowerPoint here, and I guess I got to share my screen again. That's easy for me to say. And talk about why we would ever want to use something like this. Well, here's one of the reasons that we would like to use something like this. I think if you have most spreadsheets, and I believe that in Python and I know Excel, that you at least have things such as a uniform and a Gaussian random variable. And I don't know how they are in some languages, but what I've seen is you use the term rand, at least in the Excel spreadsheet, and that gives you a normal random variable over the interval from 0 to 1. And if you use something like random n here, n for normal, which is for Gaussian, it gives you a Gaussian with a 0 mean and a standard deviation of 0. No, it's standard deviation of 1, I should say. So it's a mean of 0 and a standard deviation of 1. Now, this is typically what's available to us, and I'm sure there's advanced things which allow us to generate other types of random variables. But what this transformation on the random variable allows us to do is to generate other random variables. For example, when x is uniform, the log of x gives an exponential random variable, and we'll show this. So in other words, if you're in an Excel spreadsheet and you do rand of something, that gives you a random number between 0 and 1. If you do the logarithm of it, and I believe this probably should be minus the logarithm, and I'm not sure what it is in, I think in the Excel spreadsheet, you have to do minus the log of rand. And then you have to tell the base of the number. Something like that. Anyway, the point is if you take the natural logarithm of a random number, guess what? All of a sudden you get an exponential random variable. You get an exponential random variable. If you do a random variable between 0 and 1, and you take the tangent of that random variable, you get a Cauchy random variable. That's what we're saying here. You get a Cauchy random variable. So therefore, it allows us to generate other types of random variables other than those which are normally available to us, which include the uniform and Gaussian. Again, I'm sure there's statistics packages which allow you to generate Erlang random variables and gamma random variables and beta random variables and all these other different ones. But this is basically the simple way in which it's performed. And knowing the theory behind it, I think is useful. Here's here's the basic, here's the fundamental question that we can ask. Suppose that we have, let me at least maximize the screen here. Suppose that we have a uniform random variable, okay? So we have a uniform random variable, say between 0 and 1. In fact, let me do it down here. Here's a uniform random variable. That is between 0 and 1. We want to come up with a transformation, a g of x, so that this random variable, which only goes between 0 and 1, transforms to a given value or a given distribution. This is the case, by the way, typically in engineering. We present analysis a lot, and then we get to the point of synthesis. So this is a synthesis problem. So we want to find out what the distribution of f sub y of y is. Now, the point is that here we know what this is. We know what we're starting with, and we know what we want to end with. And what we want to synthesize is this y is equal to g of x. It's a design problem. We start off with the f sub x. We want to find out what this f sub y is, and we want to find out the nonlinearity which transforms one into the other. Now, it's clearly going to be some sort of function. By the way, it turns out these transformations are not unique, and I'll illustrate that in a minute. But we're looking at a simple transformation that does allow us to do this. And let's suppose that we required ourselves to do a strictly increasing random variable. That restricts things. Here is the interesting part. You notice that we know what f sub y is. We know what this function is. So this is an exponential, or this is something which is kind of weird. The question is what is this result? I will prove it to you now that this is equal to f sub y. In other words, the cumulative distribution function, the inverse of the cumulative distribution function for the random variable that we want to evaluate. Now, this looks weird because it looks like we're putting probability into the value of g f sub x. Not necessarily so, because f sub y is a given value. So there's no reason that if we know that this is an exponential, we know what the cumulative distribution function is, and we can figure out its result. Notice this is the same thing as the inverse of this function. This is let's see, this would be f sub, I guess this would be a function of y. No, that wouldn't do it. That wouldn't do it. Let me try it again. This would be a function that would look like this. The reason I redid this is I did it wrong because we know a cumulative distribution function has to go between 0 and 1, right? So we know that if this is equal to e to the minus y times a unit step, then we know that f sub y of y is equal to y, or 1 minus e to the minus y. It's like a capacitor charging up, right? And notice this curve. Remember when I took the wipe and I showed you what the inverse was by flipping around the piece of paper. If we take this and flipped it appropriately, we would get this curve. This is the inverse. This is the other side of the sheet of paper. This is the other side of the sheet of paper when we showed how do we get the inverse from the forward. Remember, every strictly increasing function has a unique inverse, and this is the unique inverse corresponding to this value. So we can literally figure this out. This is equal to x, and so we can solve for y. So what does the y become? Well, e to the y is equal to 1 minus x. And that means that minus y is equal to the log of 1 minus x. And therefore, y is equal to minus the log of 1 minus x. So that is the expression that we have here. If we want this exponential to be here, this has to be minus the log of 1 minus x. So we always get this random variable. So according to this derivation, if we set x is equal to a random variable between 0 and 1, we took 1 minus it, we took the log, and this is, by the way, the natural logarithm, and we subtracted y. This would be equal to y, and this would be equal to a exponential random variable. Y would be an exponential random variable. So that's how we can generate or synthesize random variables in this fashion. We've illustrated it for this, for the exponential. We've done it for the exponential. Now, the interesting thing about this is that it is not unique. Let me give you an example. This is an almost trivial example, but say that we had an f of x that went between 0 and 1. It's a uniform random variable. And we have a g of x up here that we bounce it off of. And our desire is to get an f sub y which is also a uniform random variable from 0 to 1. This is a very degenerate case. Clearly, one of the nonlinearities that I can choose is I can choose this as the nonlinearity, correct? In other words, just y is equal to x. Then every little probability mass in f sub x would bounce up to the exact same probability mass in f sub y. But I maintain that I could also do the same thing with an alternate curve. And this alternate curve is going to be this. It's going to be a TP, if you will. And that would give me the same exact result, wouldn't it? Here's my f sub y. And why would it give me the same result? Because this left probability mass would be mapped by this portion of the curve into something that was 1/2 from 0 to 1. Whereas this probability mass, which I'll denote by dots, will be transformed also to the same interval it'll be transformed to the same interval. So notice it's still a transfer of one probability mass, a uniform distribution to another one. And it's the same exact result that we got in this first case. Let's call this case A. And let's call this case B. So case A and case B gave us the same exact results. And you can see that there's no shortage of different nonlinearities that I could use. I could use, for example, this nonlinearity. just a bunch of ups and downs, and that would still map this uniform nonlinearity into another uniform nonlinearity. This would be, for example, C. And so therefore, the y is equal to g of x is not unique. It's not unique for a given target. We can sometimes restrict g of x to be strictly increasing. If we do that, maybe that restricts the result into giving just one possible g of x. Okay, how are we doing? We doing okay? Any questions at all? Well, I'm going to take a pause and refresh here.
Dr. Marks, I was curious, we know that these solutions aren't unique, but can we say something about the complexity of the curve? Like in the examples that we looked at, we had like a straight line, and then we had a triangle, and then a sawtooth function. Is there something that we can say about like the order of the polynomials that make up those functions? Like there's a specific polynomial order that will lend the same results?
That's a very interesting question. And I would answer it in the following, as opposed to trying to put a metric of complexity on the y is equal to x. I think you could talk about things such as restricting it to be well, for example, you could restrict it to be a strictly increasing function. And all of a sudden that takes your possibilities down to typically just one result, or a strictly decreasing function. Or you could probably restrict it to be a piecewise constant function. That would reduce the number of solutions. And so it would be constraints of that sort that I would apply, as opposed to any sort of metric of complexity. I guess in a way, those are metrics of complexity, depending on what your definition of complexity is, though, right?
Yeah, cool. Thank you.
Okay, great. Any other questions? Okay, we have a few minutes left. Let's go ahead and plow ahead and talk about the next topic, which is synthesizing random variables for a different point of view. This is as follows. Given a density function, we want to find out a nonlinearity so that the result is uniform. Before we did the opposite, we took something which was uniform and tried to transform it into something which was arbitrary. Here we're taking something arbitrary and trying to transform it into something which is uniform. Why might we want to do this? Well, let me just throw up a hypothetical. Suppose that there's a mathematical statistic package that is really applicable to only cases where you have uniform random variables. And it's a very powerful mathematical package. It might be worth our while to take all of our data and try to reestablish it, re-look at it in terms of a uniform random variable. So that would be the case here. So here, the examples are not unique either. But here we have a similar sort of case. We have a y and we have an x. And we have an arbitrary probability density function. And again, it's backwards of what we did before. So this is some sort of density function, right? And what we'd like to do is we'd like to come up with a transformation on a random variable so that f sub y of y is equal to something which is uniform on the interval from 0 to 1. This is the function turned sideways, of course. And the question is, what function, what y is equal to g of x do we use here in order to afford that transformation? Well, it turns out it's kind of something similar that we saw before. And that is, if we restrict ourselves, it's unique if we restrict ourselves, I believe it's unique if we restrict ourselves to something which is strictly increasing, to y is equal to f sub x, I'm sorry, f sub x of x. Really? That's very interesting. Well, the idea is you know the density function for f sub x, so therefore you should be able to generate the cumulative distribution function for x, right? And you use this exact cumulative distribution function of x as the nonlinearity. And if you do that, everything is mapped into the interval from 0 to 1 uniformly. And that is pretty slick if you think about it. That is pretty slick. One of the homework problems that I will be asking you to do is to prove this and also to prove the previous one, which is mapping a uniform random variable into an arbitrary probability density function. And the proofs are not difficult. They're weird. They're weird because you're used to thinking of f sub y's of y's as probability density functions, but now you're using these as arbitrary functions too. And so you're interpreting them in two different ways, and that can be a little bit confusing, but it's something which can be done. Okay, so again, this is the way that we take an arbitrary probability density function and transform it into something which is uniform between 0 and 1. Notice the beautiful mapping that the distribution function for x goes on forever, right? But it is restricted to the values from 0 to 1. So no matter what probability mass here that we choose, it is going to be redistributed here somewhere on the interval from 0 to 1. So we have possible from 0 to infinity mapping between 0 and 1, and that mapping gives us a value which is a uniform random variable between 0 and 1, which is really, really slick, I think. Okie dokie. Well, there is homework assigned in the spreadsheet for next time. So are there any questions on that homework? I didn't get a chance to ask you that. Okay, well, if there's none, then I will ask you the questions on the homework from next time, and we will see you then. So until then, until next time, be of good cheer. Okay, bye-bye.